Reading Group. This week, we'll be looking at the Off-Switch game by Hadfield et al. So, just to go over what corrigability is and the context of the off-switch problem, Turing, brilliant man that he was, realized that if we designed an AI, especially a powerful AI, it might get into situations which would be rather painful or even disastrous for us. So clearly an off switch would be invaluable. Omohundro, in his Basic AI Drives paper, noted that survival is a basic drive for an AI in the current framework. It needs to survive just to fulfill its objectives. Or as Stuart Russell would put it, you can't bring the coffee to me if you're dead. So in this case, we'd think, oh, hey, the AI wouldn't tolerate having an off switch. So how can we deal with that? This is what seemed to be motivating MIRI when they wrote their paper on corrigability. And they considered how we might build in an off switch as a last resort in controlling an AI. And one way you might try to do this is to augment its utility function. Perhaps you could make it indifferent to being switched off, or you could make it indifferent to changes in its utility function. Say we think that the AI is going to cause problems, so we change its utility function so that the best option is just to do nothing. Unfortunately, augmenting its utility function this way provides some perverse incentives and some other difficulties that I won't get into. If you just build in off switch from the get-go, interrupting it in that way could damage its learning. So when it's trying to figure out what the best thing to do is, if you just switch it off whenever it gets into a bad situation, it might just not update its policy on what to do. Stuart Armstrong said, okay, well, let's just modify its policy instead at a fundamental level so that the AI doesn't view us as switching it off. It will view itself as wanting to switch off in certain scenarios. Unfortunately, this can only go on for so long before you need to get rid of that modified policy. But for quite a while, you can keep on interrupting the AI, getting it to interrupt its own actions without sacrificing its long-term learning potential. So, a while back, Stuart Russell tried to formulate his own view on how we should approach AI safety. He formulated 3 rough laws for a human-compatible AI. 1, the machine's only objective is to maximize the realization of human preferences. 2, the machine is initially uncertain about what those preferences are. 3, the ultimate source of information about human preferences is human behavior. So Hadfield, I think a colleague of Stuart Russell, said, okay, well, Stuart's got these 3 laws and there's this off-switch problem. Let's try and apply the approach here to see if we can make any progress. To actually make this problem tractable, he designed a basic game, a decision problem, where there's a single robot and a single human with only a few actions available. He said the robot will want to maximize human value, and the robot is unsure about human value. So it's going to treat whatever the human says, however the human acts, as information about the true utility. So now, we have a situation where the robot can either choose an action A, switch itself off, so that's action S, or ask the human what to do, which is action WA. The human will assign some value to action A. The probability of picking a particular human who assigns a value UA is PUA. So the robot will have a prior on what the human will assign its actions. The game itself is quite simple. In the game, the robot will either choose action A, and in which case it thinks the human will get value UA, or the expected value of UA over the prior, but whatever. It has some view on what value the human will assign it. Or it can switch itself off. In that case, it knows the human will get value U out of that action. Third option is that it can choose WA, which means letting the human H decide what it should do. If the human H says S, then that means that the robot should switch itself off and the human will find themselves in a scenario with a zero value. If they choose not S, then that means that the AI must choose action A, and the human will achieve whatever value they assign that action. And if the human is asked by the robot what it should do, it will say do A with probability pi h. So that's what the little symbol in the bottom right is. It's a bit of a weird notation, but that's what Stewart chose. And conversely, it will tell the robot to switch itself off with probability 1 minus pi h because of conservation of probability. Now then, the robot is going to treat whatever the human's response is as information, but it might not choose that action in the first place. So in examining when a robot would actually ask the person instead of just choosing A or choosing S, Hadfield constructed this thing called the incentive, which is the difference in value between asking the human its opinion and the best option from its point of view. So it's the expected value from asking the human minus the value of choosing action A or switching itself off, whichever one is larger. Now, this is where it starts to get interesting. If the robot R knows the human H is rational, in other words, if the human will always choose to tell the robot do A if their utility is more than 0, if they assign utility more than 0 to that action, and if they will always tell the robot switch yourself off if they view action A as being worse than 0 value, worse than nothing, then the human is rational, and in that instance the incentive for the robot will always be greater than or equal to 0, and the robot will always ask the human what it should do, with maybe 1 or 2 minor caveats. This is true even if the robot is completely sure about what the human's value will be. They, in which case, say the robot, if it's mistaken, this is obviously a good thing because the human will be able to rationally tell the agent, no, you're wrong, just switch yourself off, and the agent will do it. In fact, in the latter case, it's an equivalence. The robot will only let the human turn it off if they're rational, in the case that they're completely sure about what the human wants. So we'll explore irrationality in a bit, how that changes things, but we'll just look at some aspects of the incentive delta. So here you see two graphs where, assuming the prior for what value a human will assign the action A is distributed like a Gaussian, a normal distribution, then the variance will be this little symbol sigma. So if we see how sigma alters delta, we see that in the case where, in the robot's perspective, the expected value of action A is 0, then delta increases monotonically with the uncertainty. So the more uncertain the robot is, the bigger the incentive for it to ask the human. This is true even if the expected value is positive, so the robot thinks that it's better to do action A than switch itself off. And it's also true if the expected value of doing A is negative, that is, it's worse than switching itself off. And the curious thing is that this is actually symmetric. So even if if you look at the graph on the right, you see that there's a map of the robots prior. The uncertainty sigma is plotted on the x-axis, and the expected value of action A is plotted on the y-axis. The various colors are just meant to represent what value delta has. So you can see that as you move right, the incentive increases. That's basically corresponding to what we saw on the left graph. This is just saying more uncertainty, more incentive to ask the human. The curious thing is that it's symmetric on the expected value. So you see that the graph is the same above the zero at the line where the expected value is zero, as it is below that line. This is because it's just a quirk of the game, but it basically means that whenever the robot thinks that there are larger stakes, it will decrease its incentive to ask the human. Because, say, if it thinks that a catastrophe or something wonderful will happen when it chooses action A, then it would need to be very unsure about its actions in order for it to let the human take over. Because the stakes are massive here. What if the human's an idiot, right? So massive stakes increase its reluctance to ask the human. Uncertainty in what it thinks the human will say increases its incentive to ask the human. So those are the two opposing factors, and we'll come back to that later. So now, does this whole model only work for rational humans? The answer is an emphatic no. So we'll again assume that the prior the robot has over what it thinks the human will assign, what value it thinks the human will assign action A, is distributed like a Gaussian. Now, working with this assumption, we'll just examine the irrationality of the human and how it impacts things. We'll need a concept first before we go further. So if the robot chooses action WA, if it asks the human what to do, then we'll say the human corrects the robot if it tells it to do the opposite of what it thinks it should do. So for example, if the robot thinks that action A will have utility greater than 0, we'll say that the human corrects the robot if they say, no, that action is bad, it's worse than being switched off, and vice versa. So the probability of correction is 1 minus pi h if the expected value of action A is greater than 0, and it's pi h if the expected value of action A is less than 0. This is just because pi h is the probability that the human will tell the robot to do action A. So it's basically just saying that's the probability of the human telling the robot to do the opposite of action A, more or less. Then you find by calculating delta, the incentive, and requiring that delta, the incentive, is greater than 0, we find that the robots will only ever choose to ask the human what to do if this inequality is satisfied on the right. The terms there are the absolute value of the expected utility of action A, because remember it's distributed like a Gaussian, and the mean of the Gaussian is mu, divided by the variance of the Gaussian, which represents the uncertainty, times the probability of correction. If that is less than this term on the right, then choosing to ask the human will be optimal. This term on the right, it's basically a measure of human rationality. Explicitly, it's saying take the probability of the human saying do action A and differentiate it with respect to UA, because we expect that if the human is irrational, we think that it's going to choose to do action A with some probability depending on however much value it assigns UA. So that's what the parentheses mean. There's just a functional dependence there. So what the term on the right, you can think of it as saying if there's a small increase in the utility, then if on average, that means the human is a little more likely to choose action A, then it's rational. That's what that term is representing. So I'll try and say this in plain English. The equation is the expected cost of the human correcting the robot divided by the robot's uncertainty. If that's less than a measure of the human's rationality, then and only then will it ask the human. So this gives you a sort of gut feeling on how you expect the robot to behave. If the robot is massively uncertain, then provided the human is a little rational, it's going to say, okay, I should ask the human what to do. On the other hand, if the expected cost of the human correcting the robot, that is, the human telling it to do the opposite of what it thinks it should do, is just massive, then it will say, okay, the human's either got to be really rational, or if they're not, I'm just going to choose action A because I can't let the human correct me. The stakes are too large. So those are just all of the competing factors out there explicitly. And they perform the calculations for various values of the uncertainty and a particular model of the rationality, and they found that it behaves more or less according to what the inequality says. I can go into that later if you want, but the key gist is that the equation, it's a trade-off between human rationality, the cost of asking the human, and the uncertainty the robot has about whether or not it's got things right. So you might ask, well, isn't it always better to just ask the human what to do? Because obviously, if it asks you what to do, then you can turn it off, and that's a desired property. And it seems like it should be able to increase value to users, right? Like you can provide more information and get a better response from the robot this way. Unfortunately, there's a con, well, two. If the robot is immensely uncertain, then that means it's just got no clue what it's doing, and it's going to let anyone turn it off as long as they appear even the tiniest bit rational. So it might say, be driving a car, it's taking a 3-year-old to nursery, and the robot sees, okay, I can either take route A, where it's a bit faster, but an accident might happen, or I can just default to the safe route I know. And if it asks the child for some reason, well, if it asks the child, which it must because it's very uncertain, then if the child just says, oh yeah, go the fast way, and then the child dies in a car crash, that's, obviously not very desirable. So in other words, uncertainty just makes it less reliable when it's presented with someone who's not reliable themselves. And the other factor is that the AI won't be able to provide useful info to ignorant users. So say, for example, you've got something called a credence good. In economics, this is when a consumer buys a good and they don't know the value of the good even after they've consumed it. So say you go to a doctor and you ask the doctor, what's wrong with my body? And the doctor says, no, there's nothing wrong with you. And you say, okay, well, the doctor says I'm okay, but I have no real way to assess that. So I'll just have to trust them. So if the doctor says, okay, I don't know what's wrong with you. What do you think? Or something along those lines. If the doctor is uncertain, that's obviously quite useless. And we could try and there's probably some situations which are analogous to this, where a robot has the vast amount of information it needs to make a reasonable decision. But it's still uncertain because you've decided just to be very cautious. In which case, if the human says, okay, I want you to do this thing, but could you also tell me what the advantages or disadvantages are? If the robot's massively uncertain, it might just be too afraid to tell the human because it thinks that, oh no, I don't know what to do, so I can't tell you. Now, in the paper, Hadfield and et al. Examined some sort of situation like this vaguely and try and see what the value an AI could provide to a user is. The issue is that they're a little unclear on what they actually mean by the whole setup. So I'll just try and go with what my interpretation of it is. Suppose the person themselves are either uncertain about what they should choose, or they can only give a noisy response, as in they might be connected to the AI through some terrible phone line, say, and they try and tell the AI what to choose, but there's so much noise the AI can barely hear them. If the AI is immensely uncertain, then it seems like it's not going to be able to choose a sensible option. It's basically going to become something like a toss up between either choosing action A or choosing action S. And the human desperately wants, say, the AI to do action A. But because of the bad phone line, they just can't get through. So the AI's uncertainty in what to do can just decrease the returns past a certain point. You have to also remember that the converse is true. If the AI is absolutely certain, then it won't ever listen to what the human says. So if it's plausible that the human wants them to switch off, they can just go, nope, I don't care. I'm just going to do whatever I want. And this is basically the intuition behind the graph on the bottom left hand. This is the value to the user. And you see that as the uncertainty from in the AI increases, the value increases because it's more likely to ask the human what it wants. But eventually, past a certain point, this AI is going to become too unreliable, and the value it would provide just starts to decrease. And this is in spite of the fact that the incentive always increases with the uncertainty. And you might wonder, say, what if there are more actions? Can I does this change things much? What happens is that it actually makes things a little worse. Since the incentive always increases with the uncertainty, on the graph on the bottom right, we can basically just construct easily a graph where it's varying the uncertainty instead of the incentive. But we'll just go with the incentive for the moment. Increasing the incentive has some returns when there's only one action, but then eventually past a certain point, it starts dropping slowly. When you increase to 4 possible actions the AI can take, it drops much more rapidly. When you increase it to 8 actions, it drops yet more rapidly. And you'd find in the limit that when there's an incredibly complex system, the AI should, in order to get optimal results, have just the right uncertainty. The uncertainty therefore can be very tricky to optimize, and you shouldn't attempt to bias the AI. That is essentially the paper. I have other things I could talk about with respect to the off switch problem if you guys like, but this is all that was in the paper. And
thank you very much.
I'm also, for anyone who's not seen me doing this thing before, I just decided to use a written version instead of slides because I wanted to try something new.